will give those. So if you get an email from me, that's what it is. And it's Zoom, and it's a free thing. And so just play along, right? So not so surprising, we're going to talk more about equilibria, okay? Equilibrium constant expressions. And actually, to kind of set the stage, we're going to talk about solubility. We kind of have a varying degrees of solubility. These are just like generic names. If somebody says something's infinitely soluble, that means it's really, really soluble. And remember when we talk about solubility, what we're doing is, here's my beaker, okay, here's my solvent, okay, it may be water, okay, it doesn't have to be water, and then I'm going to try to dissolve some. This is my solute. So these are solid solutes. I'm going to sprinkle solute in there. And I'm going to say, does it dissolve? Question mark. Okay, so that's the issue of solubility. Well, your solute dissolving your solvent to make a solution, right? So just generically speaking, if it's not infinitely soluble, it could be highly soluble, which means it's not as soluble as infinitely soluble. It could just be plain old soluble. Because you guys know that, like, if you were making Kool-Aid, if you put too much sugar in the water, right, eventually you get like a sludge at the bottom. So sugar's not infinitely soluble in water, right? Moderately soluble. Then we start to get to it's not very soluble. So sparingly soluble, right? Or just downright insoluble. Now, I'm going to go ahead and emphasize insoluble. Actually, what is this, part 5? Most of part 5 deals with materials that are insoluble. So my point here is, just because it says insoluble, it does not mean that none of it will go in. Okay, so sparingly soluble is more than insoluble, but even insoluble, some of the solute will dissolve in the solvent. So speaking of ionic compounds and nomenclature, there are, and I don't know how to advise you to memorize this, but there are some rules, solubility rules, that you probably want to memorize. I'm not sure how to advise you. So I have like maybe 4 or 5 slides on just generally how do you look at a salt. And remember, we use the word salt for ionic compounds. So a salt will have a cation and an anion, right? So for instance, if your cation is sodium, potassium, lithium, or ammonium, those are, of course, 1A plus ammonium. Okay, if that is the cation, then that salt is soluble. Okay, if you look at the anion portion, if the anion portion is nitrate, chlorate, perchlorate, or acetate, okay, then your salt is soluble in general. But this is kind of how how it goes. You see the red coming up. If your anion is a halogen, chlorine, like sodium chloride, okay, chloride, that's soluble in water. Bromide, iodide, your salt is soluble. Now, exceptions just for the halogens is if you have a cation, if your cation is silver, if it's your mercury 1 polyatomic cation, or if it's your lead 2 cation, then those things are going to be insoluble. So we deal a lot with, and actually in your lab on Thursday, you're going to be working with the chloride of silver. Okay, so silver chloride, according to this, is insoluble, and it is. Okay, but otherwise, sodium chloride is soluble. See how that works? Most salts of sulfate are soluble. Some exceptions is when the cation is calcium, strontium, barium, or lead 2. And then those are going to be insoluble. So for instance, sodium sulfate, soluble. Calcium sulfate, insoluble. Okay, so speaking of insoluble, looking at these polyatomic, well, I guess they aren't all polyatomic because we have a sulfide and oxide. But in general, if these are your anions for your salt is insoluble. Exceptions are if your cation is ammonium, potassium, lithium, or sodium. And then they'll be soluble. Okay, so like calcium, if we pick on carbonate, you know, Some of these things you already know, like chalk, calcium carbonate, insoluble, right? Okay, sodium carbonate, soluble. So, welcome to my world, I know. It's like, really? Okay. So those were rules of solubility. So I'm gonna focus on insoluble salts, and I'll kind of show you why that is. Why would you focus on something that doesn't dissolve? Well, there's a reason for that. But somewhere along the line, you want to kind of get those rules of solubility under your belt. All right. So when we say something's insoluble, I told you it does dissolve a little bit. So here's how we would show the solubility of something that's insoluble. Check it out. From left to right, basically you're taking the solid and you're going to dissolve it in water. How do I know you're going to dissolve it in water? AQ, right? Okay, so this is talking about how do you dissolve an insoluble salt. Now notice that it's going to break up, and the number of, if this is written as, this is your cation, this is your anion, okay, notice that you'll get X cations, right? Okay, and you'll get Y anions. Does that make sense? And if you kind of think of the crisscross method, actually the charge on your cation will be the, how do I say this? Yeah, the charge on your cation will basically be how many anions you have, okay? And the charge on your anion will be how many cations you have, kind of how that goes. But put another way, these are stoichiometric coefficients. Stoich coefficients. Right here. Okay, and that's important. Stoichiometric coefficients. They came from here. When the stuff dissolves, what do you got? Right? Again, this is an insoluble salt, but the cool thing is it goes back and forth. So here's mine. I think, it seems like we talked about this before. If this is your beaker, and it's a little beaker, okay, and you got liquid there, okay, basically if I put a picture of some sludge on the bottom, this is my sludge, so I'll put a little S there, that's my solid. Basically a little of that to a certain extent is migrating or breaking its ionic bonds and going into its AQ phase. Okay, and some of it is falling back down, precipitating back out. So that kind of back and forth is what we see here. Okay, so hopefully you buy that it's an equilibrium. It's a back and forth sort of thing. That's what equilibria are. But let's move on to what we've been talking about. We said you can write an equilibrium constant expression. Remember, solids don't appear in our KC expressions, so check this out. The equilibrium constant expression for this thing is simply the molar concentrations of the cation raised to its stoichiometric coefficient, which is X, times the molar concentration of the anion raised to its stoichiometric coefficient, which is Y. That's it. And we talked about, Kc are equilibrium constant expressions in terms of molarity. Kps are equilibrium concentrations in terms of partial pressures, Kps. Now this is a KSP, and it's specific for insoluble salts. We actually are going to call these Ks, these equilibrium constants, solubility products. And product means to multiply, okay? So actually, we're multiplying the molar concentration of the ions times their stoichiometric coefficients. Okay, so here's another K, but it's an equilibrium constant. It's another equilibrium constant specific for insoluble salts. Solubility product constant. So one of the things I'm going to try to convince you of is you want to be able to kind of write something dissolving. So over here on the left, you're going to have your solid. Over there on the right, you're going to have an equilibrium with its ions. So KSP expressions. So the KSP is the solubility product constant. Okay, you look it up on a table for a given temperature. It's related, but don't confuse it with the out-and-out solubility of a salt. I don't know if you remember when we talked about, what were we talking about? But we had a table that's had different, it's a temperature, the temperature dependency of solubility. So basically we had a curve for different salts. And remember, one of them was endothermic or exothermic, I can't remember. But anyway, when we talked about solubility, this was, let's see, this was grams of solute or salt per 100 grams of water. Remember that? And then actually we had it by temperatures over here. And we had various curves. Most things, when you heat them up, the solubility increases. In one case, it went down. Okay, but I'm just trying to remind you that actually that is solubility. Okay, how much can you dissolve in 100 grams of water? That's solubility. And we will talk about that coming up too. But the solubility product constant is not the same. All right, so let's look at some equilibrium constant expressions specific for the solubility product constant expressions. So you figure you have one Ag and one Cl, and they break apart into an Ag plus and a Cl minus, right? So the KSP expression, that's usually what I call it, equilibrium constant expression, or the solubility product constant expression, is just the molar concentration of Ag raised to the first power times the molar concentration of Cl minus raised to the first power. That's it. Another one, Ag3PO4, so that's silver phosphate. Notice that when it ionizes, that's kind of its dissolving process when it goes from a solid into its cations, or excuse me, into its ions, cation, anions. We have 3 silvers and 1 phosphate. So don't be fooled that the KSP expression, okay, KSP then for that salt, the ionization of that salt, or the dissolving of that salt, is the molar concentration of Ag plus raised to the 3rd power times the molar concentration of phosphate raised to the 1st power. Okay, remember, solids don't appear in our equilibrium constant expressions, so they don't appear here either. All right. So especially in lecture on Wednesday and Friday, we'll be talking more about this. But these 2 clear solutions, one clear solution is silver nitrate, soluble. One clear solution is sodium iodide, also soluble. So what we do is to take those 2 solutions and mix them together, and an ion exchange reaction occurs. So remember what ion exchange reaction is. So basically, and like I said, we'll be talking more about these, but what's going to happen is, where did they go? So your silver is going to go with your iodide, okay, and your sodium is going to go with your nitrate. They're going to swap partners. Okay, and let's see, which one do we think is insoluble? Silver iodide or sodium nitrate? I'm thinking silver iodide. Because remember, I said silver chloride is insoluble. Silver iodide is also insoluble. AgI. And just kind of get in the habit. What we're going to do is when you see something milky white like that, does it look like a solid? It is a solid. And actually, we're going to precipitate. That's what we call that. And I abbreviate it a PPT. Okay? So that's kind of what we got going on, an exchange reaction. Your Ag, oops. Oh, goodness. Oh, my goodness. Now I did it. I just think that's so cool. You take 2 things that are soluble, minding their own business, you mix them together, and you get something that's insoluble. Okay, but more on that later. These are KSPs. That last column are KSPs. The first column is the salt that's dissolving, and the middle column is the equilibrium for the dissolving process. Okay, so these might come in handy. I have a few of these. I guess I didn't have a few of these. All right. So, let's do a problem. Dealing with a salt, lead 2 chloride, that is insoluble. Okay. We say it's insoluble, then give the solubility. How's that? Okay, so it's not in terms of grams per 100 milliliters of water, but it's in terms of moles of lead 2 chloride per liter of solution. So they give this to us and they want us to come up with a KSP. They give you solubility, that's what that is. This is solubility, and we're supposed to find the KSP from that. Well, I would always start this problem like this. If I'm ever grading a problem like this, and if I don't see this chemical equilibrium, all sorts of flags go up for me. Because to me, you can't think through it unless you write down the equilibrium of interest. So it's an insoluble salt, but it does dissolve a little bit. So we write PbCl2 solid in equilibrium with Pb plus 2 plus 2 Cl minus. Okay. So the equilibrium constant expression, again ignoring the solid, right, is just the molar concentration of lead 2 times the molar concentration of the chloride squared. This is another time when it's really easy to lose that 2. That 2, of course, is the coefficient from the chloride ion. So how I usually work this, a problem where you're given what we're given. We were given solubility and asked to find KSP is this. I'm going to write underneath this right here, I'm going to write the solubility. The lead 2 chloride, they said it was 0.0162 molar. That was its solubility. But do you see where if you take 0.0162 molar of your lead 2 chloride and it dissolves, you get, since the coefficients are 1 to 1 to 2, you get 0.0162 molar of your lead 2. And can you see where the chloride ion, you get 2 times 0.0162 molar for your chloride ion. Does that make sense? Just because of how it breaks apart. So honestly, it's about that complicated. So all you're going to see me do on my slides here then is to take this concentration, stick it in there for our KSP expression, and take this concentration and stick it in there, and I will try like the Dickens not to forget that I have to square that. And that will give you what we're after. That's how you get your KSP. That's it. Okay. So we can use basically stoichiometry. The fact that you have if you have 1 mole of the salt, you're going to get 1 mole of lead 2 and 2 moles of chloride. And plug those in. And so if we set the KSP, which is what we're after, is equal to the molar concentration of the lead 2, 0.0162, times the molar concentration of the chloride, which was 2 times 0.0162 or 0.0324. So that's where my 2 times came from. This is twice of this. That's my chloride ion. We can't forget the square. Okay, round it to 3 sig figs. Then your KSP is 1.70 times 10 to the negative 5th. Now, one thing I forgot to emphasize was, remember what we said, the smaller your equilibrium constant, the smaller your Kc, then that means you have less product. The smaller it is, you have less product. And what our product is our dissolved salt. So kind of keep that in mind too. All right, so these will be due, and we're going to do the next assignment slide, and then we'll call it a day. These will be due on Wednesday. Let's take a look at these. And have a whole lot of hints, which is good, right? So these 3. This is the first one. Kind of go through my bells. Okay, so you have 4 problems to work. It says write the KSP expression for these equilibria, and notice that they're showing you how the salts break apart. And so yeah, this one's not too bad, is it? Basically, we need to take the silver ion squared, okay, times the sulfate ion raised to the 1st power. That's it. That's all you got to do for that one. So you're a quarter of the way there. The next one looks like this. Okay, where it says write the solubility equilibria, write solubility equilibria equations that are described by these KSP expressions. So I did the first one for you. So the first one says, all right, solubility product constant expression looks like this. The molar concentration of Fe3 plus raised to the first power. So that must mean I have 1 mole of that, times the molar concentration of the hydroxide iron raised to the third power. It must mean I have 3 moles of that. So then kind of you just got to go backtrack and write what the solid is then. That must be Fe quantity OH3. So it's not too bad, but that's kind of how I would do that. And then the last one, the following KSP values are found, given to you. And you're supposed to write the solubility product constant expression to which these apply. It just seems so, the wording seems kind of strange to me. So they give you an example for silver chloride, but if we look at chromium 3 fluoride, this is what I would like to see you do. I would like to show you have you show me the ionization. Okay, show it going from its solid state into its dissolved state. Okay, and then I would like to, once you get it there, I want you to write the expression. So the expression is the molar concentration of the cation raised to its stoichiometric coefficient times the molar concentration of the anion raised to its stoichiometric coefficient. So I'd like to see, that's what I'd like to see you do. I know it's a little different in their example, but I want to see the equilibrium, only because I care. All right, so back to lecture. Yeah, those are already pushed out there. I know, I'm like really with it today. Okay. So, KSP, the solubility product constants, right? I said that the smaller it is, then that means the less product you have, and the less product is the dissolved, the ionized solid, salt. So you can kind of estimate a solubility, but we're going to talk about why you can't just directly look at a low KSP and say, it must be very insoluble. Very, very insoluble, right? KSPs are cool because just like with the silver iodide a little bit ago, we could have anticipated that an exchange reaction between those two clear solutions, we could have anticipated that silver iodide would precipitate out just by looking at its crazy low KSP. Okay. And then this last one, this is kind of fun. We'll get to this probably on Friday, maybe on Wednesday. But you can look at salts, I mean, you can look at their KSPs, and you can know, given a choice, which salt will precipitate out. So I'll kind of look at that. All right. So, is this the next one? Yes, it is. So just like we looked at before, solubility changes with temperature. How much salt is going to be dissolved in water changes with temperature. So also KSPs change with temperature. So unless otherwise stated, we're going with the 25 degrees Celsius, which isn't that thermodynamic standard temperature, I think. So here are a bunch of KSPs, right? So actually this is 2 tables in one, not really 2 tables in one, okay? And it's alphabetical. So you can get a sense for things that are very small, aluminum hydroxide, for instance, you would think is, with such a low KSP, would not be very soluble at all. Something with a, calcium hydroxide, more soluble. Continuation, this is the one I had 3 slides. Okay, alphabetical. KSPs if you need them. Okay, so let's work another type of problem. The other type of problem we were given molar solubility before and we knocked out the KSP. In this case, we're given the KSP and we're supposed to knock out the molar solubility, so it's kind of backwards. And actually, I made some notes in my office because I want to use an ice table, an ice chart for this one, okay? Remember what I said I would start with, and I'm always suspicious if students don't do this. I need to see you write calcium carbonate, solid, and I need to see you show it ionizing, okay? I don't think you can work this problem without doing that. I really don't. Even though when it comes for the test, I won't say that you need to do this. This is what you need to do. So we were given the KSP, and we're supposed to find the molar solubility. Let's see, how did I do this? Of course, we can now, once we have it written like this, it's easier to write the KSP expression, okay? So KSP is equal to the molar concentration of calcium raised to the first power times the molar concentration of carbonate, also raised to the first power because there's their stoichiometric coefficients. The KSP was given. All right, so here is my ice table. I don't know why they always give the crazy, well, we'll just go with the cute little surrounding thing. So, remember with your ice tables, what you guys have been doing is you write a column for the reactant, in this case, the solid, and 2 columns for the products. So it looks like this. And this always kind of makes me giggle. I don't think all chemists do this, but I'm going to write the molar concentration of calcium carbonate, solid. That's okay. I don't belong to anything that would try to kick me out, I don't think. Okay. Move it over a little bit. Then I'm going to write the molar concentration of Ca plus 2. And I'm going to write the molar concentration of carbonate, CO3, 2 minus, or minus 2. And then the whole beauty of ice tables go like this. We have initial, change, and equilibrium concentrations. Okay, basically we're going to take initial, apply a change, and come up with equilibrium concentrations. Now, doing an ice table for this sort of problem is a little bit of overkill, but actually it will help you with the other things we do with equilibria. So now, this is probably unique to me, so I apologize in advance. Basically, I use an infinite amount of solid. Basically, I'm going to end up with a sludge at the bottom. So I have an infinite amount of solid. Okay. In this case, before I start, I don't have any calcium and I don't have any carbonate. That will be different in Wednesday's or Thursday's lecture because we'll have a common ion in there. Actually, I guess it'll be different in Wednesday's lecture. Okay, do you see where if I let X be equal to basically my molar solubility, X equals molar solubility. Okay, then I can go ahead and my change is going to be minus X to my infinity, right? Okay, and do you see because the stoichiometry is a 1 to 1 to 1, actually I'm going to increase by X for my calcium ion and I'm going to increase by X for my carbonate ion. So infinity minus X is, as far as I can tell, infinity. 0 plus X is X, 0 plus X is X. So that last row down there, my point is, that last row down there is, and the first one, that does not appear in the equilibrium constant expression. But now I have, now I can substitute these X's back into my KSP expression. And that's exactly what I'm going to do. So let's see what my builds do. Okay, so this is without an ice table. I think a few slides from now I can use the ice table for the same problem. But if we let X be equal to the amount of the solid calcium carbonate that dissolves, then at equilibrium, X will also be equal to the molar concentration of your calcium cation because it's a ratio of 1 to 1, and also the molar concentration of your carbonate ion. Then, like you might be imagining, all we got to do is take those X's and substitute them in for our equilibrium constant expression or our solubility product constant expression. Okay, and so X times X is X squared. Don't need the quadratic for these, right? I can get to the value of x by taking the square root of 2.8 times 10 to the negative 9th. Two sig figs, then x is 5.3 times 10 to the negative 5th, and we're going to go ahead and put units of molarity there because by definition that is our molar solubility. So that's the molar solubility of this salt given that KSP. So KSP and molar solubilities are not necessarily the same. So this actually is, I believe, how your textbook would do it. Notice what's missing is that first column with the calcium carbonate solid. Okay. But otherwise, it's the same, where they have initial change and at equilibrium. Okay, and so remember how this works is you take the initial, apply the change, and come up with equilibrium concentrations. Same thing. All right, so let's do another one. And I'll do an ice table for this one too. Okay, so it's a different salt. Okay, notice it's going to be a little different because when it ionizes, you're going to get 2 Ag pluses and 1 CrO4 2 minus. So we're kind of bringing in stuff that we talked about in Gen Chem 1. Of course, that's silver chromate. So calculate the molar solubility given this KSP. Again, I will be very disappointed or surprised if you have to work this problem and you don't write this equilibrium constant expression. To get to molar solubility given the KSP, to me you need to write, I'll go ahead and put this other thing down there. You need to write the chemical equilibrium, so solid on the left side and how it ionizes on the right side. Make sure you pay attention to the relative numbers of moles of everything. And a really common mistake, and I think this one's probably come back to haunt me before, is you need to recognize, like I said, you have 2 moles there, 2 moles there, okay, and of course that ends up squaring the molarity of your Ag+. So nothing new here. Again, KSP was given. So here is my ice chart. And it's going to look a little different. Oops, that isn't what I wanted. Yeah, I guess I did. Okay. So my columns, probably a little different than your textbook. The first column is going to be the solid. That's your Ag2CrO4S. Ag2CrO4S. I know it's strange. You're like, molar concentration, really? But that's okay. The next one is going to be simply Ag+. The next column is going to be your CrO4 2 minus. And then along the side, we're going to have rows of initial, change, and equilibrium concentrations. So your solid, like we did before, it's going to be an infinite number, okay, an infinite quantity before initially, and actually at equilibrium. In this case, and again, we're going to change this up tomorrow or Wednesday when we lecture. But in this case, we're just plain water. So the initial molar concentration of your silver, zip. The initial concentration of your chromate, zip. Okay, and so it usually, I'm going to go ahead and say let X equal the molar solubility. It doesn't hurt to go ahead and clearly say that. So if that's the case, then at equilibrium we'll have minus X to our infinity there. Okay, but can you see where actually, if you look at the balanced equilibria, what goes right here? In terms of X. Does that make sense? Very good, 2X. And then what goes over for the chromate? Just X. Perfect. Very good. At equilibrium then, we have 2x for the silver and x for the chromate. And we can take those and substitute them back into our equilibrium constant expression. Okay, so we said KSP is equal to the molar concentration of the silver squared times the molar concentration of your chromate raised to the first power. And this is a really common mistake. Okay, we don't bring along the squared. I'll say we. Okay, but that's the other reason why to work in these you really need to write the equilibrium, write the KSP expression, and go ahead and solve in terms of x, substitute back in your KSP expression. All right, so now we don't have to use the quadratic again, right? Because this is going to work. But make sure that you apply that 2 through your quantity 2x. Of course, that would make, 4x squared, right? 2x quantity squared is 4x squared. 4x squared times x is 4x cubed. Okay. So now, basically, and I can't remember how my notes go, but what I would do is divide both sides by 4, okay? To get x cubed is equal to some number. Divide both sides by 4, and then somehow you're going to want to be able to do this. You need to take the cube root of it, and you can do it a couple different ways. I think a good way is basically to, finally you get to use that x to the y power key, okay? So where you're basically going to raise it to a cube root is the opposite of cubed, kind of. So a cube root would be raised to the 1/3 power. So you're going to want to be able to do that. So you can play around with that. 2 sig figs, your molar solubility then is 6.5 times 10 to the negative 5th moles per liter. Yay, another good thing you get to play with your calculator on. Your cheap calculators because you can't use the good calculators in here. Okay, so that's the molar solubility of silver chromate, given the KSP. So this is to kind of take a look at why the KSP, which indicates solubility, doesn't always jive with relative solubilities. And it has to do with how many particles it breaks into. So here we have, let's see how do I say this, because I'm going to actually, we call this A, B, where basically you have one cation and one anion, calcium carbonate respectively, and actually this is an A2B, where you have 2 cations and 1 anion. That's kind of the form it takes. But anyway, just not looking at the substance, but looking at their KSPs, you would think that something that's as small as 1.1 times 10 to the negative 12, you're like, wow, that doesn't favor, that's very low on the products. So you would think that the solubility of this second one is less. But the molar solubility actually is a little bit more. The molar solubility of the silver chromate with the lower KSP actually is just a little bit more, 6.5 times 10 to the negative 5th instead of 5.3 times 10 to the negative 5th. Okay? So the problem is you have kind of a different pattern going. But these all have patterns. You see what these are all just A, B, because you have one cation and one anion. So actually, as they're written with kind of decreasing KSPs, that so also is as they're written with decreased solubility. So if they're the same pattern, you are comparing apples to apples. Okay? If they're not, then you really can't directly compare the KSP with the solubility. So as you might imagine, we do kind of, aside from the ice tables that I encourage you to set up and all that, I guess I should say for this sort of problem, even though I would do an ice table, you can, if you understand the pattern, apply the pattern. So if you always have one cation, one anion, actually you can get to molar solubility from the KSP this way, okay? The molar solubility is always going to be the square root of KSP. It's true. Where X is the molar solubility. So I'm okay if you want to go that route. There's advantages to the ice table. And if we do another one where this is, instead of A2B, this is actually AB2, and you'll end up with a very similar sort of deal. Okay, if you were to go through, let X be equal to the molar solubility of AB2, actually then you end up with, this might look familiar with the problem we just did, where if you can get to the molar solubility, X, if you take KSP divided by 4 and take the cube root of it. Okay, so that works. And actually for your last homework, I'm going to kind of redirect you back there to that. So there are these patterns, but I'm not good at memorizing things. So take a look at these, 4 and 5. The B. Okay, 4 looks like this. Okay, calculate the aqueous solubility. Actually, aqueous solubility, that's molar solubility. Calculate the molar solubility in moles per liter of each of the following given KSP. So it's exactly what we were doing. Let's see what I do here. Oops, that isn't what I want to do. Come back. That's for Wednesday. It only does what you ask it to do. Okay. So in this case, I didn't make an ice table. I just said if your molar solubility is equal to X, then you have X of barium ion formed, X of chromate formed. So X squared is equal to KSP. Find the value for X and, find the value for X, and that's your molar solubility. I think you're okay with this. The second one looks like this. Now this one, I went ahead and gave you quite a few details because I looked back at my notes to remember how I did this. So basically, given the KSP values, which you can look up anywhere, but I'm going to go ahead and give them to you, given for these 5 salts, these KSP values, you're supposed to go ahead and arrange them in increasing molar solubility. Okay? So to me, and I look back at my notes, the only way I know to do this is basically to do 5 problems and come up with the molar solubility, and then go ahead and compare the molar solubilities. So I went ahead and gave you the general form again. Remember, we just talked about a minute, if you have one cation, one anion, then X squared, it's equal to your KSP. So the square root of your KSP is your molar solubility. The only other pattern we have up here is A2B in this last one right here, and you can knock out the molar solubility this way. So I would come up with 5 molar solubilities. That's kind of the only way I know to do it. And once you've got the molar solubilities, you can answer the questions, but you can't answer that question with just KSPs. You could, I guess, if you didn't have that last one, couldn't you? Or, you know what you could do? You could go ahead and rank these that are AB. Does this make sense? Rank the first 4 that are AB according to their, their KSPs because of the same pattern, right? Their solubilities would be relative because they're the same pattern, and then bring that one in. Okay, that's a better idea.
So we don't have to solve for X for all of them?
Yeah, so you wouldn't have to solve for X for all of them. All you need to do is kind of resolve the last bit about this -5, where does it, you have to know where it inserts though. I don't know. Your problem. But on my key, I came up with 5 molar solubilities. Okay? Fun and games. That's all I have.
You take
I know. There's something there, I really think.